The other functional group that we're going to look at that has a single bond to oxygens is the ethers. There are no hydrogens attached to the oxygen in ethers. You have carbons on either side of the oxygen. So basically you can say ethers are an oxygen with two alkyl groups bound to that oxygen. Because there are four groups on that oxygen, just like in an alcohol, you're going to see that there is a bent bond there. This bent bond is at an angle of about 109.5, just as in the alcohols. This is a polar bond. The carbon-oxygen bond is a polar bond, and it gives ethers a small amount of water solubility, not a huge amount. They have slightly higher melting points and boiling points also because they have some polarity in the molecule. But again, it's not huge, just slightly greater than that of the alkanes. Notice this compound cannot hydrogen bond, so its intermolecular attractive forces are not as strong as those in the alcohols. They only have dipole-dipole forces. That's why the water solubility is lower and the melting points and boiling points are higher than the alkanes, but not as high as the alcohols. So here is a little diagram that shows how physical properties change from the alkanes to the ethers to the alcohols. These three compounds all have about the same molar mass. Butane has no oxygens in it. The only intermolecular attractive forces that they have are the van der Waals forces, or what we call the dispersion forces. If I look at the ether in the center, there's an oxygen, and it is a polar compound, but no hydrogen bonding occurs. So it has the dipole-dipole forces, or the permanent dipole forces. So its boiling point is slightly higher than that of butane, but not hugely so. If I look at propanol, it has a hydroxyl group in it that allows it to hydrogen bond. That is a very strong intermolecular attractive force, so you can see that its boiling point is quite high compared to the other two. Ethers are named differently than the alkanes, alkenes, alkynes, and alcohols. Ethers are named in a common way by basically naming the alkyl group on one side and the alkyl group on the other side. Now, there is another way of naming them, but we're not going to look at that because I just don't want to give you too much. So this is a common way of naming the ether. If we look at the first example on the left, you can see there is a methyl on the right-hand side and an ethyl on the methyl on the left-hand side and an ethyl on the right-hand side. So we call this ethyl-methyl ether. Now, why did I put the ethyl first? Because it's listed alphabetically. If I look at the compound on the right, you can see there's an ethyl on either side, and instead of calling it ethyl-ethyl ether, we call it diethyl ether. Go ahead and use the same methodology in naming ethers of identifying the alkyl group on either side and name this ether, and then draw dicyclopentyl ether, remembering that you have to use the name to figure out which alkyl group is on either side. To do this ether that's written here, the first thing we do is we recognize that it is an ether because there's an oxygen with a carbon chain on either side. Next, we identify what are the two alkyl groups. I see that on the left I have a propyl group, and on the right I have a methyl group. So I write propyl. and then I see that there's a methyl on the right-hand side, so I put methyl. Notice I put the methyl first and the propyl second because you're supposed to put them in alphabetical order. Now to draw the dicyclopentyl ether, I first will know that I have to have two cyclopentyl groups on either side of the oxygen. Draw the two cyclopentyl groups. I put the oxygen between them to make it an ether. Ethers are used as anesthetics. You probably hear the word ether and you think of the first anesthetic that we used to have, which was diethyl ether. These will cause a loss of consciousness and a loss of the sensation of pain, but diethyl ether had some problems. It caused a lot of nauseousness and it was difficult to control. Now they have some new ethers that have halogens on them. Notice fluorine and chlorine on these ethers down here, and these are the modern ones that we use today for anesthesia.